So let's start the session. So today's topic all about your Savart Law. Okay. So as your earlier classes, earlier session, you learned something about uh, property of magnetic field lines. So anyone can you tell me what is the properties of magnetic field lines? Anyone? No one? Okay. So I'm saying something about that. So first of all, the magnetic field lines are originated from your north pole and it is terminated at your south pole. Okay. So this magnetic field are originated north pole and is terminated at south pole. These magnetic field lines are forming a closed loop like this. So these are magnetic field lines traveling from north to south. These magnetic field lines are never intersect each other. Am I right? So this exactly the mesh work. It's from a closed loop. So it is never intersect each other. The quantity, the strength of magnetic field line at the pole, that means your north pole and south pole is maximum. That means when we are moving from away from the magnet, you seems to that your magnetic field are minimized. That means your magnetic field are maximum around the magnet, and when you are moving from away from your magnetic field strength are both decreasing. Okay. So this is your structure of your magnetic field lines. See, this is your north pole, this is your south pole. Your magnetic field are travel like this, and this line which are drawn is a closed loop structure. They are never intersect each other, and this is show the direction of your magnetic field line each and every point. Okay. Okay. So let's say this your right hand thumb rule. So as comes your right hand thumb rule. Okay, just give me. Okay, sorry for that. Okay. So just tell me, what is your right hand thumb rule? Because if I'm not wrong, you are learning in your lower classes, right hand thumb rule. No? Right hand thumb rule, Fleming's rule. Am I right? Kyle, Josna, where it all students, Maya, Parikshit. So what is your right hand thumb rule, my dear students? Someone telling? Yes.
It is used to determine the direction of magnetic force.
Magnetic force. Which one rule? Right hand thumb rule or Fleming's rule, my dear student?
Right hand thumb rule.
Okay, no problem. Anyone else? Okay, no problem.
Right hand thumb rule is used to determine the direction of magnetic field lines in a straight line. For example, we can hold the current carrying conductor in our right hand, where the thumb is facing the direction of current. Then the way we wrap around the conductor, that shows the direction of the magnetic field lines around the conductor.
Very good, Parikshit. Is said perfectly correctly. So see guys, friends, if I said this is your current conducting current and wire, if I put this is my right hand, if I put the right hand like this thumb is indicate the direction of the current, and this curl finger is indicate the direction of magnetic field. That means if I said my current flowing upward, that means my magnetic field into the paper. See, this is the into the paper. Getting? If I said my magnetic field is towards the downward, so my current is out of the paper. That means it's leaving the paper. Getting? So in the your right hand thumb rule simply say that the direction of your magnetic field. Clear this point? All of you? Dhamesh, you said properly, correctly, but the mistake is it is not right hand thumb rule, it is right hand Fleming's rule, where we use for finding the current direction and force. So you see something like this, it is visible, 3 directions. So this is the force, this is the magnetic field, and this is the direction of current. Clear, Dhamesh? Work? Okay, very good. So we move further. So I just write here. So your thumb use the direction of current and your finger, which is curl finger, gives the direction of magnetic field. Okay, so let's move further. So what is the importance of Biot-Savart's law? So first of all, you know what is a Biot-Savart's law? No. So how can we say what is the importance of Biot-Savart's law? So let's connect with this Biot-Savart's law, your previous concept. If I said there is a point charge plus Q present, okay. So if this charge is present, so can you tell me what is the electric field around this? There is any electric field present in the plus Q charge? It is possible any electric field present around the plus Q charge? If it is yes, then how do we find out this electric field?
Ma'am, we can find the electric field by bringing a charge, test charge near into the electric field of the plus Q charge. We can use the formula E equal to F by Q naught. Find it.
Very good. E is equal to F by Q naught. Very good. And someone else, Josna. No, Josna, I'm sorry. Jotsana. Okay, no one. Dharmesh. Okay, no one. Parishit, correct? Yes, dear. Unmute yourself. You heard something law about this to finding electric field around a positive or negative Q charges. The word of the law. This is one law which we used. It's called Gauss law. If you remember, no. If there is any point charge are present around that, so we need to say there's a Gaussian surface, and at the Gaussian surface we find 1 upon 4 pi epsilon naught Q by R. This is are related to Gauss law. So similar manner, the Gauss gives the law to find electric field. So similarly, your Biot-Savart's, the scientist, gives the law to find magnetic field around a conducting wire. Okay. So can anyone tell me what is the definition of a current? What is a current? What is a current? Okay, student, don't worry. The current is simply charge by time. Okay. So when we are saying charge, that means at rest. At that time, we are talking about on electric field because it is a rest motion. But when your charges start moving a current, right? So when it is create a current, your magnetic field is introduced. Getting? So your charge by time, that means your charge is performing a motion, charge are doing a motion, so your current are introduced. And when your current is introduced, your magnetic field are introduced. So scientist is simply called as a Biot-Savart's law. This gives the application to find a small current around any conducting wire. What's the meaning of conducting wire? So if I said a conductor and the current I is flow, then around this conductor we get a magnetic field. So this relation, it is implied by your Biot-Savart's. Okay, clear this? Okay, so we move further. So this is your first of all the symmetric charges. So what's the meaning of symmetric charges? What is the meaning of symmetric charges? All of you are present, or only 2 students are present? It seems to like. No problem. So what is your symmetric? So see student, if I said this is your closed circuit or this is your loop, and if I said the positive Q charges is present here, that means on the surface of your this spherical, all charges are Q. So that means your charges Q are spread all over the system. Very good. It is a simply continuous distribution. So charge distribution, perfect. Harish Mahesh, perfect. So it is a simply a continuous charge distribution. So continuous charge distribution is simply called as a symmetric current. So when we are saying we have a conductor, and that in that conductor your current I is flowing, that means in that conductor you have symmetric charges are distributed over this conductor. So you get each and every point same I. That means if I said, let's say this is my conductor, so I get I here, the same as here, the same as here. That means this conductor are your symmetric charge distribution and symmetric current distribution. Clear? The word symmetric. Okay. Now, so we start your magnetic field due to current carrying conductor. So first of all, how we find the magnetic field? So we know that if we have a wire, and this wire, in this wire current is flowing. That means your current is flowing, that means here your electricity is generated. So if you take your any iron piece near to this conductor, it attracted by this conductor, because due to this current in this field there is a magnetic field is generated, right? So if you take any iron piece near to this conductor, you seems to like it is attracted or sometimes repelled by this conductor. That means this conductor behave like your magnetic field. Getting? So now this conductor, so if I say this is tip part, is the current flowing in this direction. That means we apply our right hand thumb rule. So what is right hand thumb rule? We hold the conductor like this. If my current going upward, it seems my curl finger shows inside. See, this is your inside part, right? That means my magnetic field going into the paper. That means it's penetrate inside. If I said this is my conductor and I hold conductor like this, so it showed that your magnetic field is leaving. Getting? That means out of the paper. Getting this point? So similar manner, if you learn something about students, electric field. So our electric fields travel from positive to negative. Am I right? So on the basis of your current direction, you said your electric field travel positive to negative. Similarly, we have two types of magnetic field direction. One into the paper, one out of from the paper. So if I said into the paper, that means this is a conductor, this is curl finger. If I said out of the paper, that means this is a conductor and this is. So your current is downward, your current is upward. Getting? Okay. So magnetic field through a conducting current circular loop. So this is simply, if I said here a point Q present, okay, around this, let's say I said this is a conducting wire. In that wire, I current is flowing. So what is the current? What is the magnetic field at point B? Sorry, at point P. What is the direction of magnetic field? Can you tell me? Anyone? I said this is my conductor. The current I flowing upward. This is the point P. So my question is, what is the magnetic field at point P? Into the paper. Very good. Similar manner, if say, let's say this is my conductor I, and here a conductor, another conductor of I. Okay. Now let's consider a point P, a point Q, a point R. So please tell me, what is the magnetic field at P, at Q, at R? One by one. Anyone? Unmute yourself and tell me. Dharmeshwar, you try? You try? No problem. It is, if it is mistake, I will rectify it. Just try to say Kyle, Shrutika. No one? Unmute yourself, friends.
I'm in point Q, the direction of magnetic field is outside the paper. In point R, that is also outside the paper.
Yeah.
At point P, if the distance between the two wires are equal, I mean, if point P is present in the midpoint between the two wires,
Yeah.
it will I think the magnetic fields will cancel out.
Okay. So you said the magnetic field is cancelled out. So at point P, there is no field is present. Okay. Clear? All of you agree with this? Do you look horrible? No, no, I guess. So unmute yourself. Tell me. Say that the answer. No one interested. Okay, no problem, students. I know this is the first lecture. You are uncomfortable to interact me. Don't worry. The teacher will be come as soon as. Okay. So let's start. So first, we consider at point Q. See, students, when we are considering at point Q, put your hand at this finger. This conducting wire. So if I put my conducting wire, so it's look like something this way. That means this is your curl part and this is your thumb. Right? This, am I right? Diagram is shown properly. So this shows, put your finger and show. Where is Q point is indicate? It's outside. That means your curl finger indicate, this point indicate it's outside. So it is correct. Now put your finger at I. Let's say this is your I1, this is your I2. Put your finger I2 and consider return your Q point. So if you see, so if I said due to I1, magnetic field is out. Fine. Okay, I will read right. Okay. Just give me 1 minute. No problem. So here we write due to I1, magnetic field out. Okay. Now put your finger here. So if you put your finger here, you seems to write your curl finger like this and your all finger like this. Am I right? So it seems to like you're in this direction, your Q point experience due to I2, magnetic field be inward. Am I right? Clear this point first of all, students? Clear? Okay. Now similar manner we consider R. So if I consider R, it seems to like R is outward. So sorry, in outward, yeah, exactly, outward. So it seems due to your I2, magnetic field is outward. Now consider I1. If I consider I1, see, if I consider I1, it seems to like this is your point, this is your magnetic field. It seems to like this. So it shows outward. It shows inward for I1 respect. So I write here due to I1, it's inward. Clear first of all this point? Clear this point? So when there is a 2 conductor, when there is a 3 conductor, don't consider only with respect to one. Consider with respect to both the conductor. Getting? Okay. Now consider P point. So due to at point P is between of I. So if I consider my I1, so it's conduct current and in this. So it seems to like this one and it seems to like inside. So due to here, if I said I is magnetic field inside. And when we are saying the outward, so here your due to I2, magnetic field is outside. So if it is in between, exactly distance are same, the currents are same. So your B point experience no magnetic field. Similarly, your Q point also experience no magnetic field. Similarly, your R point, but it is a distance are vary. So they last me. That means your Q point and your R point experience a magnetic field, but your P point are not experience any magnetic field. Clear this? R in outward. Exactly, Ravi Kumar. Clear this point? Parishit, any doubt? I guess you are not understanding. Should I repeat?
I'm clear.
Should I repeat? Okay. So now, when we are saying a magnetic field, we know that in the magnetic field there is a n number of coiling. That means if I said this is my wire, sorry, this is my conductor, I say we coil a wire, and in this wire we flow a current. So this current I is flowing. So this conductor have some length, let's say L be the length, and in this conductor we have put some n number of coiling. So this coiling is increase your strength of magnetic field. For example, if I say this is my conductor, I coil only 2 wires. That means a small amount of current will be flow. So small amount of your magnetic will be produced. If I coil here 100 tons, that means you increase your coiling 100 times. So you will increase the strength of the magnetic field. Getting? So this number of coiling also affect your magnetic field. Now see strength. The strength of magnetic field at the center of coil, it depends on radius of a coil, number of turns in a coil, and strength of current flowing in a coil. Now what's the meaning of a center? Up to here we are talking about only on the conducting wire. Okay. So now if I said, let's say the point P are presenting here, or my conducting wire is not a straight wire. We are considering this is my conducting wire. Sorry, this is my conducting wire, and the point P here, and we say the conducting wire flowing current I. So find the magnetic field at that point. This is your condition for a straight conductor. Easy. But now if I said instead of this straight wire, if I just mold this conductor, that means it seems to like this. And if I put a point P here and say this is a current I flowing, find magnetic field P at this system. So this curve path is simply like this. So this is your P point. Clear? So if my conductor, it is not a straight, because it is not always conditioned, your conductor should be straight. Maybe this is a wire, we mold a wire like this, any structure, like this is a, if this is a wire, we mold a wire like this. So if my conductor, it's form any arc like a structure, or we can say it's form on any circular structure, at that time, it's depend on how many coilings are done over here, what is the distance of this N, and the strength of your coil. That means what is the current flowing in that coil. Getting? So this all also affect your magnetic field. We are not up to here on Biot. We are simply seeing what is the main terms in a Biot, where we apply, where we use. Now we have a derivation part also. Okay, so just take. It is not a theory lecture, I know. Okay. So we move further. So see, when we are saying magnetic field due to moving charges, already we say magnetic field is created when the charge start moving, because when your charge at stationary. So if I say this charge is present here. So here if charge is present, so you say electric field is produced, and due to this electric field, your charge start moving, and when charge start moving, it produce current. And due to this current, your magnetic field are generated. So this is simply conversion of electric field to a magnetic field. Getting? So when your charge start moving, it simply flow your magnetic field, and the direction of this is simply the current, show the direction of current, and the curl part and the circular part is show the direction of magnetic field. Clear this? Clear this part? Okay. So now we have a different type of structures. At that structure, we find what is a magnetic field and how our magnetic field are flow. So see, if I say this is a my structure, this is my coiling, it is not your resistance, it is your conductor. You know, inductance, inductor. Okay, no problem. You seen to this? What is this? What is this? And what is this? What is first one? Just type. If you are not comfortable to unmute yourself, just type. It is also okay. What is first one? This first one, the second one, and third one. Second one is cell or battery. Okay, okay, no problem. I guess it's the diagram mistake. See, I'm not drawing like this. This is cell or battery because this is a positive, this is a negative. If two plates are like this, parallel to each other, what is called? Capacitor. Yeah. Harimesh, perfectly. Capacitor. Parikshit, okay. What is first one? Resistance? No? No problem. The first one, yeah, exactly. Ravi Kumar, it is a resistance. This is a capacitor. And the third one, coiling, inductor. Okay, no problem, no problem. It's called as an inductor. So we have a resistance, capacitance, and the third one is your inductance. So what is the inductance? Yeah, exactly, Josna, inductance, dear. So what is the sorry, what is the inductance? Sorry for disturbance. What is the inductance? So inductance is simply the part where is a coiling is provided. So in that coiling, your current type flow and creates a magnetic field. So you seen something when you are AC circuits where we use at that time we are use inductor because our inductor are active component where our resistance are passive component. Getting? So at that time we use our inductors. Okay. So see, if I said this is any structure, this is any arbitrary structure and I want to find a current. So if there is a I current flowing, so we simply say if there is a I current is flowing, so around this we get a magnetic field. We get a magnetic field like that. Similarly, if your current flowing here, we say around this a magnetic field is created. Getting? So this shows if your magnetic field into the paper, its direction like this. If your magnetic field out of the paper, its direction seems to like this. So if we say any part of the conductor, we simply use your right hand thumb rule magnetic field direction. So magnetic field always produce in a closed loop. Therefore, we draw structure like that. Clear this point? Okay. So now famous law which is called as a Biot law. We deal so many parts. Now we actually imply that all parts we are still till learning, and then we find what is actually use of Biot law and why we are using a Biot law. Okay, students. So let's a simple question. Let's imagine this. If I said this is my conductor, and at point this is visible to you, students. This point is visible to you properly. So let's say this is the first point. If I said what is a magnetic field at here and then I put a point here, what is a magnetic field here? That means I put the 2 points, let's say these 2 points, the first point and the second point. So the simple question, if this is my conductor, so what is a magnetic field at my first finger and what is a magnetic field at my second finger? It is same or different? That means if I put a conductor, the point P1 here and the point P2 here. So my simple question, what is the magnetic field at point P1 and P2? If it is same, then why? Okay, Ravi Kumar, fine. P1 is greater than P2. Okay. That means Parikshit said it is not same. Ravi Kumar said it is same. Anyone else have another option? No one? Okay. So we move. So first of all, okay. So let's consider one example which is very similar to, if this is your bar magnet, this is your north pole and this is your south pole. If I take a small iron piece here, it's attracted by your bar magnet easily. Okay. Now, if I put a small iron piece here, it is also attracted by your bar magnet easily. That means if you are take any iron piece between these points, it's simply attracted by your bar magnet. But if you put your point here, it is not easily attracted by this magnet. Why? Because it is very far away from your magnet. That means your magnet has some strength, some field. Around that only your magnetic field are alive, students. Are you getting my point? That means beyond this limit, their magnet is not working. Because, see, in the world there is a so magnet. So all magnets are attracted each other. You are attracted by some magnet? No. Only the particular strength, particular area in which your magnetic field are valid. Apart from this area, your magnetic field is not valid. Okay. So, up to where your magnetic field valid? Up to where your magnetic field will be strong. So, for all this type of question is given to by your Savart. Okay. So, this is your use of Savart. So, in short, to find any point, if we say a conducting wire, a circular wire, any type of wire where your current is going away or coming from wire, if you want to find a magnetic field, you should apply your Savart law. Getting? So Savart law simply gives the magnitude of your magnetic field as well as direction of your magnetic field. Getting? So let's start the derivation. So we start from here. It's a very easy derivation, don't worry. So can anyone tell me what is electric field at point P and definition of electric field? Anyone? E is equal to 1 upon 4 pi epsilon naught. Electric field intensity. Okay, no problem, students. I will tell you. See, you see this formula 1 upon 4 pi epsilon naught Q upon R square. You see these formulas? No? Okay. No problem. You see this formula? What is called second one is Coulomb force of attraction, if I'm not wrong. Am I right? Okay. So see, if I set the as concerned this formula simply says electric field is directly proportional to the charge and inversely proportional to the square of distance. Am I right? So we know that if a charge is present, and the charge is from any distance, so we say r distance, so my electric field is charge by distance ka square. Am I right? So similar manner, if your current is present, so what we get? Magnetic field. So current, so according to this, if I say this is my conducting wire, in that conducting wire, if this are infinite conducting wire, so I don't know what is the total length of this conducting wire. So let's the I be the current and L be the length of the conducting wire. I want to find magnetic field at point P. So according to your Savart law, it simply states that, so connect the dotted line, and this line is simply called as a distance. We, instead of consider total length of the conductor, we consider a small length which is called as an infinitesimal small length, and this length is called as a dl, which is called as an infinitesimal length element. So we consider small length element. So instead of finding total magnetic field due to conductor, we find a small magnetic field due to small length of, and then we integrate over the system. So see, so we say my dB, that means small magnetic field, is directly proportional. So what is the current flowing in that length? It is simply I. So we get here total I dl. Okay. So my magnetic field is I dl. This is your length. So we say dB is inversely proportional to R square. Clear this? The statement are clear first of all, students? Hello students. Okay. So if I equate this to simply dB is directly proportional to I dl upon R square. Now your dl is a length element. So if I write R over here, or we can say the cross product of R. So I also multiply R in denominator. Simply dB is directly proportional to I dl into R times R power cube. This is also one form and this is also one form. Clear here? So now, according to your Bio-Savarts, your dB is directly proportional to length. Your dB is directly proportional to small length instead of length. This is small dl. And if we know that dl into r is nothing but we write dlr sine theta because it is a cross product. Okay. So this is your cross product. So if we put dlr sine theta, that means your dB directly proportional to I dl into r upon r power cube is becomes dB I dl r times sine theta upon r power 3. Now see, this r and r one power get cancelled. So we get dB directly proportional I dl sine theta upon over r square. Now this is your Bio-Savart's law. We know that in every law there is always proportionality constant. So remove the proportionality constant, we use some constant, and this constant is simply defined by, like your electric field, you know K is equal to Q by R square. So this K is called as a proportionality constant. So similarly in a magnetic field also, we have a one proportionality constant which is mu naught by 4 pi I dl sine theta over r square. So this is your total Bio-Savart's law. Clear this part? Hello students, clear this part? Okay. So now, can anyone tell me what is a mu naught? What is the name of mu naught? Hello. Hello. No. Epsilon naught is your permittivity of the free space which used in a electric field. And mu is when the current is flowing in the conducting wire, my dear student. So it is not a mu naught. It is a mu naught, but it is not a mobility and it is not a epsilon naught. So the name is something different. It is related to permittivity only. No one? Hello. Okay. Say anyone. Parikshit, Kayal, Yadzira, Sai. Josna. No one? All of you? Okay. So, Mubable, Ravi Kumar. Unmute yourself, friend. Okay, no problem. So like your epsilon naught, it's called as a, epsilon naught is called as a permittivity of medium. So what is defined? Where our electric field is present, where our electric field are generated. In that medium, we use a constant which is called as the K, is nothing but your 1 over 4 pi epsilon naught, and this epsilon naught is called as a permittivity of a absolute medium. So like your mu naught is called as a permeability of a medium or free space. So for electric field purpose, we use epsilon naught, and for magnetic field purpose, we use permittivity. It's okay, Ravi Kumar, no problem. Clear this? So see, so according to your derivation, we simply get what is dB. So dB is equal to mu naught upon 4 pi I dl sine theta over r square, and this mu naught by 4 pi is called as your permittivity of the medium. And what is a sine theta? So see students, in this diagram, this component is describe your angle theta, and this is simply IDL. Okay, so this is your theta angle. Clear it? Clear these points, all of you? Okay, so now, so K is nothing but your mu naught over 4 pi. So what is our final formula? So final formula of your Biot is B is equal to mu naught upon 4 pi I dl sine theta over r square. Okay. If I write this formula instead of this, like this, dl is equal to, sorry, dB is equal to mu naught over 4 pi I dl into r over r cube. It is right or wrong? The second formula, which I write in a black page, it is correct or wrong? So this formula is also correct, because in this formula, your this product, which is dr into r, it is shows your cross product. Okay, this will show your cross product. And what is the value of cross product? So if you remember, dear students, A cross with B is nothing but AB sine theta with some angle which is in vector form. So according to this, your DL R sine theta upon R power 3, this power get cancelled, and we got IDL sine theta over R square equal to dB. Clear this point? Clear this point up to here? All clear? Okay. So we move further. Okay. So can anyone tell me what is the unit of a magnetic field? Hello. What is the unit of magnetic field? Tesla. Very good. Something another units also know, like a Gauss. Okay, Tesla. Very good. Okay. So okay, fine. What is the unit of epsilon naught? Vapor. Yeah, vapor is also unit, Josna, but vapor is not the total unit. So vapor is a unit of flux. So we say magnetic field is nothing but vapor per meter. Getting? Okay. So what is the unit of epsilon naught? It's something Newton over Newton meters. Newton. Epsilon naught is a unit of force. Sorry, force instead of force, we write Q1 Q2 upon 4 pi epsilon naught F time R square. So according to here, epsilon naught is a unit of Coulomb square per Newton meter square. So similar manner, your epsilon naught has also have a unit, and its unit is related to Henry per meter. Or sometimes it is also called as a Tesla per ampere. Getting clear this? Okay. So now, when we are talking about the vector form, so I already said the directly proportional IDL, here R also, and sine theta over R cube. So see students, when we are saying a vector form, please remember your I is not a vector. So that means your DL is a vector. We write a magnitude. So that means it shows the only magnitude of that component. Your R is a vector. Your sine will be angle, and your R power 3 is also vector. So according to this, your mu naught 4 pi is your magnitude, and it have some specific value like your epsilon naught, which have 6.67 into 10 to the power minus 11. So similar manner, your mu naught also have a value. So mu naught is a 4 pi time 10 to the power minus 7. Okay. So when we are writing mu naught over 4 pi, that means your value 10 to the power minus 7 only. Clear this? Hello. Clear this part? So mu naught value is 4 pi 10 to the power minus 7 vapor per meter square, or Tesla per meter. Vapor per ampere. Clear this? No one is present. Shrutika. Kayal. Parikshit, turn on your camera. Okay. All of you students, please turn on your camera. Hi, hello Kayal. Hello Shrutika. You all of you have a very good faces. Then why are you turn off your cameras? Please turn on. I am also feeling like I am lonely. Only saying no one can respond. Just respond, students. It's difficult. It's not getting. If it is so, please tell me which point are you not getting. I will repeat once again. All point clear, Kayal? Shrutika? Okay. So we move further. So see, now we have a formula. What is our magnetic field? So magnetic field is mu naught over 4 pi I dl sine theta over r square. Okay, clear this point? Okay, now we find what is the magnetic field due to a straight wire. Okay, so now our work to find derivation part of a magnetic field due to a straight conducting wire. So if I put a straight conducting wire, okay. So first of all, if I say the current I is flowing in that wire, I don't know what is the actual length of your wire, because it is maybe infinite length in the sense very large length. So what can we do? So for that purpose, let's we divide this section in two parts. So first part we said our wire is from infinity to infinity. Okay, from infinity to infinity. Clear this part? Okay. Okay, I will take a new blank page and I will explain here. See. Okay, I take a wire. and flowing a current I in that wire. I don't know what is actual length of that wire. That purpose I consider the length of wire from minus infinity to plus infinity. Okay. Now I divide this wire into two sections. Okay. Let's see. This is a section of the wire. So I said this is my O point. O in the sense my origin point. So now I cut this wire into two parts. One part is zero, another part from 0 to minus infinity. So instead of finding complete length, that means your dB over 0 to infinity, I also said is nothing but my dB is minus infinity to infinity. It's nothing but my dB 0 to infinity, or we can say minus infinity to 0 dB plus infinity to plus 0 to infinity dB. Now we take this 2 is nothing but same 0 to infinity dB plus 0 to infinity dB. That means we simply find, instead of finding minus infinity to infinity dB, we simply find 2 times 0 to infinity dB. Clear this point first of all? What can we do? We simply do, instead of finding infinite length, we cut our system in two parts. We take one from minus infinity to 0 and the another one 0 to infinity. And consider this 0 to infinity is a twice. That means upper part and lower part. Getting? Clear this? Now we find the magnetic field at point here. At point. Okay. This is a R distance. So we consider, let's say, this is your distance. Let's say this is R and this is your length. So this is your angle, which is a theta. Let's say this, I said this is also angle. Let's say I said this is alpha. Similar manner, if I draw the diagram downward, this is also shows same. Here another angle, let's say we say alpha, beta. So this is a theta 1, this is a theta 2 angle. Clear this diagram? What we can do? We simply do our minus infinity to infinity problem in 0 to infinity manner. So now we apply our formula. What is our formula? dB is simply mu naught upon 4 pi I dl sine theta over r square. Now tell me, what is your dl sine theta? What we use dl sine theta? Which formula we take dl sine theta? Hello. Hello. So now we find this length. So what is this length? So this length is nothing but your r square. So I just write small r here because this is unknown for me, and your capital R here. So from here we simply get small r is nothing but, use a Pythagoras. This is your L, this is your R. So according to your Pythagoras, your hypotenuse square is nothing but first angle square plus second angle square. So according to this, your r square is nothing but L square plus capital R square. So if we remove, we simply get r is equal to under root of L square plus R square. Clear this first of all length. Now put this length over here. So in this formula we get mu naught over 4 pi I dl sine theta upon, instead of r square we write L square over R square. Clear this point first of all. Now can you tell me what is a theta, sine theta? What is the angle of theta here? What is a theta? If this is a theta angle, yes. So what is the sine theta values? Sine theta, how it defines sine theta, dear? It simply defines opposite upon hypotenuse. Very good. So what is your opposite? If this is your theta, very good. Capital R by small r, very good. So see, so your sine theta is equal to capital R by small r. What is the small r value? Is 1 over under root of L square plus R square. So put this equation 2 in equation 1. So if I put my equation 2 in equation 1, I simply get dB is equal to mu naught over 4 pi I dl sine theta over r square. I write just L square plus R square, and in the presence of theta we just put the value mu naught upon 4 pi I dl capital R over L square plus R square, one part here and another part under root of L square plus R square. Clear this part? Now this mu naught over 4 pi is your I dl over R upon L square plus R square over power 3 by 2. Clear this? Now we just apply integration and we find out what is the final value. So no need to solve this type of numerical much. Just apply your formula. So for here we simply see what is our final value. So this is your dB. So we integrate. So apply integration. So after integration, this total dB. So dB is equal to mu naught. So my mu naught upon 4 pi. So mu naught upon 4 pi R I are constant. So in the integration dl upon L square plus R square power 3 by 2. And the integration goes from 0 to infinity. So if we solve this type of integration, we simply get, there is a shortcut and the formulas type question where we say this type of integration values is implies 1 over R square. Because if we take integration dl, we get R term final value. Here dB is equal to mu naught Ri over 4 pi into 1 over R square. Now R square get cancelled. We get B is equal to mu naught I upon 4 pi R. Clear this first of all, students? Clear this? Magnetic field value clear? Integration value is 1 over R square. Okay. You directly substitute. No need to solve here. Okay. It is just a trick. If in the denominator something is R a square plus b square raised to power 3 by 2. If you remember something, we put a tan inverse function substitution method in integration. So here we directly substitute the value 1 over R square, and with the help of 1 over R square we get the formula is mu naught I over 4 pi R. Okay, clear this point? Now student, tell me, this is your magnetic field because of what? Because of complete conducting wire, half conducting wire. This is your magnetic field because of complete conducting wire or half conducting wire. This is your magnetic field because of your semi-half, or we can say half, semi-half wire. So because see here, we say our dB is twice of dB, but we solve only dB purpose. So now if I put the condition, we know B is equal to 2 times mu naught I upon 4 pi R. So from here we get magnetic field B is equal to mu naught I upon 2 pi R. Please keep in mind, this is very IMP formula. You get direct question about this in your JEE entrance exam. This is very IMP. But this is formula related to your for straight conducting wire. Straight conducting wire, or for full length. And this is for your semi-half wire. Clear this two formula? It is very important. With the help of this two formula, we find different types of structures. Clear? We move further. Clear this formula? Okay. Now we consider similar manner one more equation. There we already said due to arc point. See, if I say this is your arc. So this is my arc point. Here current I is flowing and I want to find a magnetic field at point B here. So the same procedure we do like here. Put here. We say this is your R distance. This is your angle theta. So what is your dB, my dear student? Is mu naught over 4 pi I dl r square sine theta. So now, can anyone tell me how we find this type of equation? This is for your not long wire. This is for your circular arc. So please tell me. This is for your circular arc. So please tell me how we find this type of problem. Just put, students, we say we consider a small d from r distance. Okay. So we put dB is equal to mu naught 4 pi I dl r square. Now we know that if my angle is very small. So we say if your theta is very small, so sine theta approximately equal to theta. This condition is known to you, right? So if this happens, so we put instead of theta, we put just theta, right? Now take integration. So we integrate dB is equal to mu naught over 4 pi I dl r square theta. Clear this part first of all, students? Hello. Hello. I'm audible? Or if you are not able to understand this problem, just see. Just use this. If you are not know this term, just see. We know that if this is my arc point, these always say if we draw as a point here 9.9, what's the writing here? I'm not getting. Okay, no problem. So we always say this is always we draw tangent. If any curve part there, for the direction purpose we draw a tangent. Am I right? So if we are draw a tangent, we say our theta will be 90. So what is the sine 90? Sine 90 is 0. So apart from this, your theta will be gone. Now it is easy. Now it is easy. Just apply your integration formula. What is your integration? So your mu naught is upon 4 pi. It's outside from your I is also out. Then we get dl over r square. Now student, what is the value of dl over r square? What is the value of d over r square? No? Okay. See students, no problem. This is your dl. This is your I. This is your theta. Just apply. We know that d theta. What is your displacement? Sorry, your what is your angular displacement? Angular displacement formula. So it seems to like arc length over radius. Am I right? So what is your arc length, my dear students? Arc length, your I L over radius. And what is angular displacement? It is theta, d theta. So instead of dl, we write r time d theta. So now put this value in this equation. We simply get mu naught over 4 pi I integration r times d theta over r square. Now this r square get cancelled. We get mu naught over 4 pi I times d theta over r. Clear this point? Now we know that theta is not related to r, so your theta will be outside. So we get mu naught over 4 pi I upon r into theta. So from there we simply get a final value is B is equal to mu naught over 4 pi I theta times r. This is your magnetic field due to any circular loop. So if your loop are circle, that means your theta will be 2 pi. Am I right? So if I said if loop is circle or circular loop, that means your theta will be 2 pi. So what is your magnetic field? So your magnetic field become B is equal to mu naught over 4 I times 2 pi divided by r. See, pi get cancelled, 2 also get cancelled. So we get a final formula is B is equal to mu naught I over 2r. This is your magnetic field due to circular loop. And the red one is gives the magnetic field due to any arc. Clear? This is your shortcut formula. I know this is your theory part, but apart from this, now you know how we get this formula and how we apply. For that, we have a different, there is a 7 to 8 shortcut formulas on basis of this two derivation. Clear this point? Okay. So now we take see students, we are here. So apart from this, we know what is the magnetic field formula. We get mu naught. Magnetic field is simply, now see here two angles, one is a theta 1, another one is theta 2. So for that, if I want to find a magnetic field B, this crosses imply that your magnetic field into the paper. So now what is a magnetic field at B is simply mu naught over I upon r. But we know that there is a theta. So for mu naught over I upon 4 pi r, this is a magnetic field due to semi-half, because we derive this equation where we get a mu naught over 4 pi r. This is a magnetic field due to semi-half. So there is an angle. So I said this is for sine theta 1. Similarly plus magnetic field mu naught, we say mu naught upon 4 pi I sine theta 2. So if we equate, we simply get B is equal to mu naught I upon 4 pi r sine theta 1 plus sine theta 2. So this is your shortcut formula to remember. Clear this point? Okay. Now we move further. Now in this system, there is a first of all into the paper and out of the paper. So see, if the cross is indicate, that means anything is going inside the end cross. So if you see a cross, it is into the paper. If you see a dot, it is out of the paper. Clear first of all this notation? Because in the exam there is a not mention any time it is into the paper, out of paper. They just mention the dot and cross. Cross means something is out, something is coming towards us, and cross in the sense the end point. That means something is going. Getting? So into the paper, that is band, and out from the paper, that is coming us. Okay. So see. So now in the first system, there is a cross, that means there is a magnetic field, and this magnetic field is the r distance, and they want to know what is the magnetic field here. So what is the formula for magnetic field due to any circular structure? What we formula is simply B is equal to mu naught upon 2 r I time theta. Am I right? Not there's a not 2, there is a 4 pi. There is a 4 pi I r, or here your r is a small, so I write small, I time theta. Now for this is a circular loop, my dear student, this is a circular loop. So what is a theta? Theta is 2 pi. Put here mu naught over 4 pi I over theta. Instead of theta we put 2 on RC. 2 pi, pi get cancelled, 2 and 2 get cancelled. We simply get B is equal to mu naught I over 2R. Clear this first of all? This is your magnetic field due to a circular loop. Clear this? Hello? Yes, friends, clear this? Clear this point? Okay. Now see. Now if see in the first diagram, you see your magnetic field curl finger showing like this, because the arrow shows in that for your purpose, arrow showing in that. So your magnetic field is like this, right? And for second one, your arrow showing in this. Am I right? So in that it's so out of the paper, that means coming out, and the first one is shown into the paper, is going inside. Clear? I know from my side, my left is your right. Okay, so consider like that. If I show this is my left, this is my right side, so you are seeing is the left side. Am I right? For that concern, if the direction is this, it is going out of the paper, and if the direction is going into the paper. So for the first one, the diagram is indicate it is into the paper, and the second one it is indicate out of the paper. On the basis of diagram, you are able to see, you are able to say direction of magnetic field, and with the help of this formula, you are said about your magnitude of magnetic field. Clear? Okay. Now we move further. So now same manner, the same, if there is arc is formed, if there is an arc is formed, and this is a theta, so find magnetic field. So we say already the formula is mu naught I theta time 2 pi r. Okay. So if the current going in this direction, that means you're into the paper. Hello. Now similar manner, if instead of your theta in the previous one, we see something like this. This is your theta 1 and this is your theta 2. So for that purpose, you write the formula mu naught I upon 4 pi r sine theta 1 plus sine theta 2. Right? So instead of if we want write a sine theta, we want a cos term. So at that time we consider theta here. Let's see. So in this scenario, we take here alpha and beta. So my formula will be sine alpha plus sine beta is equal to mu naught I over 4 pi r. Now, if I want to take theta here, one theta here, I want to take one phi here. So my angle will be changed. So it is simply same formula. So instead of sine, I just write mu naught I over 4 pi r. So if we consider this angle, we write sine term. But if we consider this angle, we write cos. So cos theta plus cos phi. Clear this? So if you have an angle at your unknown point, that means at point P, so at that time use a sine factor. But if you don't know your angle at your unknown place, you know the angle at your corner point, use cos factor. This is only the formula. Okay. So this is also same manner. If we know this angle, we consider a sine formula. Instead of two formula, just we write sine alpha. Clear this? And the last one is due to semi-half. Takes infinity to infinity. So for upper part purpose, we have mu naught over 4 pi r. For lower part purpose also we had mu naught over 4 pi r. So if we solve this, we get 2 mu naught I upon 4 pi r, and after that 2, instead of 2 get cancelled, mu naught I over 2 pi r. This is your final answer for the magnetic field. Clear this? Clear this point? So this is your important formula which are used in your competitive exam. So only the thing is, you must remember your two formulas which we derive. The first one is B is equal to mu naught I over 2 pi r. This one, and the second one, B is equal to mu naught I theta over 4 pi r. This one. This is very important formula. If you know this two formula, you derive each and every formula which we are discussing in two previous slides. Clear this? So, okay. We go for numerical session. So, before going numerical break, or should continue? Break? Of course, I know. So, take a 10-minute break. We will continue 8:32. Okay? Okay. Hello. Let's start. Okay. All of you coming? Say, Kyle, at least in the message text, just write, are you present or not? Okay. So let's start the session. Okay, Parishit. So, as we see, so magnetic field due to a current carrying wire, circular current carrying wire or state. So first state, If it is a straight wire, their magnetic field is B is equal to mu naught I over 2 pi r. If it is full, and if it is semi-straight in the sense half part, if we are taking as a half part only, semi, at that time we say B is equal to mu naught over I over 4 pi r. So this is for semi and this is for your full wire. Okay. So now this is a question. The question is a circular arc of a metallic wire subtend as an angle, the theta is given as pi over 4 at a center. So as per your question, it simply say this is, if this is your circular arc. Sorry. If this is your circular arc. Okay. If this is your circular arc part, they say at this center, that means here, from the angle theta is equal to pi over 4 and the radius of curvature is r. The magnetic field at the center, that means this arc at point P, find the magnetic field. Clear the question? Clear question? Turn on your camera, students, and tell me. Clear question, Shrutika? Okay. So can you tell me which formula we are used to apply here? Shrutika? I'm audible, dear? I'm audible, dear? So can you tell me which formula we are apply here? It is given to a metallic circular arc. That means we have a two formulas, for one straight conductor and the second one for arc purpose. So which formula we are apply here? Sorry for that. Parikshit, can you tell me which formula we apply here? Yeah. Very good. Mu naught over 4 pi r. Okay, clear this? So we apply here mu naught over 4 pi r. Now see here, I is your current, theta is given, which is 4 pi over r. So we put here. So if we substitute the formula here, we B is equal to mu naught over I 4 pi. Instead of theta, just put pi by 4. So this pi and pi get cancelled. The 4 multiplied by denominator 4, we get B is equal to mu naught over I times 16R. Clear this? Clear this question, dear? All of you clear this question? So the simple, we just apply the formula, which is mu naught over I upon 4 pi r. Now we put the value, the given is pi over, we put here that we get B is equal to mu naught over 16R. The option, which option is correct? Option, clear this? Okay. Now move further. The second question. This is the solution of that. The second question. The two concentric coils carrying the same current in a opposite direction. That means they say one coil here and one coil here carrying a current in a same but in opposite direction. The diameter of inner coil is a half of the outer coil. They say, okay. First of all, two concentric coils and the diameter of outer is half of the diameter of inner. Okay, this is. So this is two concentric in opposite direction. So if this is a current for first, so this is a current for your second. This is the magnetic field B1, this is the magnetic field B2. If the magnetic field produced by outer coil is common center R1 1 Tesla. So from here the outer coil produce 1 Tesla, the net field at the center. So they want to know what is magnetic field at the center. So which formula we are used here? which formula we are going to use here? Can you tell me? Hello. See, student. Here we also use the magnetic field formula due to arc, which is mu naught over 4 pi I over theta. But now this is for a circular loop, so theta is 2 pi. So that means your magnetic field is mu naught over 4 pi I into 2 pi over R. Here R I forgot. So this pi get cancelled, the 2 get cancelled, we get B is equal to mu naught I over 2. Clear this first of all? Clear this formula, students? Are you there or not? Clear this? So this is your final formula. Okay, sorry, R here is missing. So now for B1, if for B1 your radius R, so for B2's radius is 2R. Right? So see, for B1, its formula is mu naught over I upon 2R. So for B2, is since to mu naught over I, 2, instead of R, we write 2R. So it is mu naught over I upon 4R. Clear this? Now, they say outer coil is a common center at 1 Tesla, the net field at the center. So what can we do here? So we simply subtract. So we get B naught is given, which is B1 minus B2. What is B naught is 1 Tesla. So what is B1 is mu naught over I upon 2R minus mu naught over I upon 4R. Clear this? If we substitute that, we simply say they given to you the common center at 1 Tesla. So the addition is simply we multiply here 2 and we multiply here 2. Okay. I just use different color to see it. Here we multiply 2, here also we multiply 2. The formula is 1 Tesla is equal to 4 mu naught I upon, sorry, instead of 4 it's 2. 1 Tesla is equal to 2 mu naught I over 4R minus mu naught I over 4R. So it seems to, if we solve this type of problem, is simply mu naught over I upon 4R, which is for half. So the correct option is C. Getting? Because it's given 1 Tesla. So it's simply the question about to derive your magnetic field formula for half. Getting? Okay. Now, like this is the solution for that. Now, this is your, now we are dealing, all the question is related to a conducting wire, right? We put conducting wire straight, then we put our conducting wire in an arc shape. Now, is a question is about your, if your instead of conducting wire, we say circular loop is present. So, like a loop, let's say let's imagine we say have a ring. It is visible to you first of all. If this ring is present, so this ring is not a ring. This is your magnetic field. That means in that system your current are flowing. If I consider this system and I put this ring at here, let's say this ring here, and I want to find a magnetic field here, that means each and every part on this ring are produce magnetic field on this part. Because we know in the starting we say we have a symmetric system. That means continuous charge distribution. So for that, this is the circular part. See the diagram. This is your circular part. In this your current I flow. So if I draw the diagram is look like this. This is your circular part. This is now your current is I flowing in this system. And we consider any small area. Let's say dl. Your current I flowing here. I consider any small area. Let's say dl over here. So if I consider dl over here and I want to find magnetic field at point P here. So for that purpose, I draw simply a point. So if I draw from here, I also need to draw here. So at the center, we must draw a line which is jointed at the center. So see, this is your known coordinate. Let's say I say this is your x-axis. This is your y-axis and the third one is your z-axis. Now, this is your r length. If this is r, this is also r. Now, at point B, there is a magnetic field. Not only at point B, you have a two magnetic fields. One going in this direction and another one going in this direction. Now, if we resolve this magnetic field, we see one magnetic field in this direction, one component in this direction. Similarly, if we resolve this another component, we get magnetic field in this direction. One magnetic field in this direction and another magnetic field in this direction. So if you see this and this cancel to each other, so we get overall magnetic field in this direction now. So this is here the overall direction. This magnetic field and this magnetic field are cancelled to each other. So now we want to find a magnetic field at point P. We simply use a Biot-Savart law. So see friends, this is your R. This X is known to you. This R is unknown to you. This is, if I said this, so this is your radius of given circular arc which is known to us. So we use a magnetic field formula. So if this R, let's say if I said instead of a capital A, R, we use a A. So if this is your A, this is your X, this is your R. So we use a Pythagoras theorem, and according to your Pythagoras theorem, your R will be X square plus A square. So from here we say A is a radius and X is a distance where we want find magnetic. Now, according to your Biot-Savart law, so due to B1, that means first line, due to this line, your magnetic field will be mu naught I dl upon 4 pi sin theta over r square. Now, this is your perpendicular length. See, in this diagram, we have this is your perpendicular at this point. So, if this is a perpendicular, your sin 90. And what is a sin 90? So, sin 90, my dear student, is, okay. So, sin 90 is 1. So, we get dB is equal to mu naught I dl upon 4 pi r square. This is for B1 and this is for dB2 also. That means for due to this line and due to this line, you get dB is something mu naught I dl over 4 pi r square. For all, because they are present in opposite sides, but their location, their distance are equal from the your circular loop. Now, if we use our sign convention form, our Biot-Savart law, which is dB, so we get dB sin theta. So see guys, this is our dB1 and dB2. Now we say already we have 4 component here in this point. Here, that means your dB sin theta 1 plus dB sin theta dB1 sin theta, and okay, I will write 1 second, just give me 1 minute. See, here you have a dB1. So dB1 is resolved in 2 components. One is dB sin theta, another one is dB cos theta. Similarly, your dB2 is also resolved in 2 components, my dear student. dB2 sin theta plus dB cos theta. dB2. Now see, I already said your this component and this component are cancelled to each other. That means this component and this component are cancelled to each other. We get simply dB1 sin theta plus dB2 sin theta, and we already say your dB1 is equal to dB2. That means we simply say dB 2 times of dB sin theta. Clear this point first of all? We simply resolve. That means at point P, we have a 4 magnetic field, but 2 magnetic field are cancelled to each other because they are perpendicular like this. Means one direction here and another direction is the opposite direction. So 2 opposite direction, they are cancelled, and the 2 in upward direction, they are add up and give a final result. Okay. So similar in this, so we get here dB sin theta. So now B is equal to dB sin theta component. So what is the dB sin theta? What is dB? So dB I get mu naught over I dl upon 4 pi r square. What is sine theta? So in this diagram, see, this is your theta. So if this angle is made of theta angle, so is opposite your hypotenuse. So what is your opposite? Alpha by a. So instead of alpha we take as a later. So we say simply a by your hypotenuse. The diagram seems like this. See, this is your r. This is your a. And this is your x. This is your r. This is your x. This is your a. If this is your angle theta, so your angle theta, what is your angle theta? So sine theta is your opposite upon hypotenuse. So a over r. A is nothing but your radius of the circle. Please keep in mind. Sometimes instead of a, they are also use z component. So it's possible. So here we get, instead of sine theta, we put a over r. So from here we get mu naught over I dl upon 4 pi r power cube a. Clear this? Now, see. So from here we simply integrate. So we get mu naught over I a 4 pi r power cube integrate dl. Because we have a length small dl in the previous section. That means this corresponding section we consider small dl. So instead of this dl, we consider a whole length. So we integrate dl. So what is the length element for a circular loop? What is the area of circular loop? It is pi r square. So what is your length for circular loop? It is something circumference of the circle, which is, what is the value of circumference of circle, my dear students? What is the value of circumference of the circle? It is 2 pi r. So it seems to mu naught I a upon 4 pi r power cube 2 pi r. Okay, but here r is not your, a is a radius. So instead of r we write a. So now mu naught over I a square, pi get cancelled, 2 over 2 get cancelled, and we get r power cube. Now what is your r? So see students, this is your r, which is unknown to us. So according to your Pythagoras theorem, your x square, a square is equal to r square. So from here, your r is nothing but x square plus a square. So if we put r here, we simply get p is equal to mu naught I a square upon 2 over, instead of r we write x square plus a square power 3 by 2. Instead of r just write under root of x square plus a square. So this is your final value of due to a circular loop. Clear this? Okay. Now we move further. See. So if I said कि my center or my observation point at the center of loop. Center of the loop, that means, see guys, see students, this is your x point, this is your r point, and this is your a point. Center, that means the point which is present at P, it is not presenting at P, it is presenting over here. That means your x will be 0. What is the formula? Is b over mu naught a square upon 2 under root of x square plus a square power 3 by 2. Now if your x is 0, put 0 here. So if you put 0 here, you simply get the power 2 to get cancelled. So we get mu I a square upon 2a power 3. This 3 power and 2 power get cancelled. The final answer B is equal to mu naught over I 2a. So this is your magnetic field if your circular loop present and the observation are taking at the center only. Clear this, friends? Hello. Clear this? Okay. Hello. So now, see, similar manner, if I say when we are taking an observation at that time, there's a two condition. One, this is a circular loop which has a radius a, and another the point x which is present a far distance. If I said my a value, a that means your circular loop radius, and x is the distance from where you want to find a magnetic field. If I said my a is very less than x, that means let's say your radius is 0.1 and your distance is something about 1 meter. So it is very large. So at that time, we simply, in the denominator, we have a x square plus a square raised to power 3 by 2. So in the denominator, instead of taking a square, we neglecting a square from denominator. So if so your formula becomes mu naught over IA, but in the numerator we can't neglect. Divide by 2x square plus a square power 3 by 2. So we neglect a square from here. So we get simply mu I a square upon 2x square 3 by 2. So this 2 get cancelled. So our final formula is B times mu naught I a square over 2x x power 3. Clear this? Parikshit? Hello? So this is a magnetic field. When your observation or observation point where we want to find a magnetic field, it is very far away from your circular loop, or we can say our circular loop is very small as considered to our point where we want to find a magnetic field. At that time, we use this formula. Clear this, friends? Hello, clear this? Hello, Shrutika, are you there? Kyle? First of all, tell me, clear this point? Okay, Ravi Kumar. So we move further. So the question, an electric current is flowing in a circular loop of radius r. At what distance from the center of axis of loop will magnetic field 1/8 of its value at the center? The question is like a simple electric field instead of electric current flowing in a circular loop. They say your magnetic field at the center is 1/8 of your magnetic field at x point. They want to know what is the value of x. That means if this is a circular loop, there x is present. So they say magnetic field at point P is nothing but 1/8 of magnetic field at point center. There is magnetic field at the center. So what is the x? Clear this? First of all, question clear? Question clear to you, friends? Hello. Question clear to you? Okay. So now the question is magnetic field at the center. So tell me, what is the procedure? How we find first of all? Okay. So we first apply magnetic field at the center. So magnetic field, what is the formula? See, for center, we say if a center, that means your x will be 0. if this so, P is equal to mu naught over 4 pi I A. See, this is your formula, friends. Mu naught I A over x square plus a square. Now see, we take instead of I, sorry, I just write formula here. B is equal to mu naught I A square over 2 x square plus a square power 3 by 2. Now your x is 0, so this term is 0. So this 2 get cancelled. We get mu naught I over 2a. So this is your magnetic field at the center. This is your first equation. Let's say I said this is B1. Now they say distance, at what distance from the center of axis your loop will be magnetic field is 1/8 of the B. So the B2 is formula is mu naught I a square over 2 x square plus a square 3 by 2. This is your B2. And the relation is B2 is equal to 1/8 times B1. This is your E relation. Clear this first of all. Now put your value in the equation. So see student, if I take a new page here, B2 is equal to B2 is equal to 1/8 times B1. So what is B2 is mu naught I a square over 2 x square plus a square power 3 by 2 is equal to mu naught I over 2a. See, this is mu naught over I 2a. So I put here into 1/8. See, this 2 get cancelled. Mu naught over I get cancelled. So from here we get a power 3. This a is multiplied by this a power 3 8 times this 8 also here. It is x square plus a square raised to power 3 by 2. Clear this first of all? This steps clear to you, all of you? Now, see students, if this so, we say 8 is equal to x square over a square divided by a raised to power 3. Sorry, I put in this term and then we say raised to power 3. So we take cube root. If I am taking cube root, what is the cube root of your 8? So your cube root of 8 is 2. So we take, here we write 2 is equal to under root of x square plus a square divided by 8. Clear this point first of all, students? Now from here we say 2a is equal to x square plus a square in a raised to power 1 by 2. Now take here squaring both sides. If you are squaring both sides, you simply get 2a square is equal to x square plus a square raised to 1 by 2 square. So this 1 by 2 get cancelled. See, this 1 by 2 and 1 by 2 get cancelled. We get 4a square is equal to x square plus a square. Put a square here, we get 3a square is equal to x square. So from here your x is equal to under root of 3 times a. Clear this? Hello, clear this problem? Now, so here there is a R is present. Instead of R, just consider A. Or if you want to put R, so in this problem put here R only, no problem. Okay. Now the question is magnetic field intensity at the center of the circular current loop radius. So they want to know what is magnetic field at the center, where your radius is 0.4 meter and your current is 3 ampere. So first of all, tell me which formula we are going to use here. I said magnetic field at the center. So the simple formula, if the center, that means your x is 0, so magnetic field is mu I over 2a. Am I right? which we are using in a previous section, just in the previous problem. So from here, we know what is I, and R is called the radius of current loop. So radius is we are taking for loop. We already said loop ray A, and the point is X. So the given B is equal to mu naught. What is the value of mu naught? So it is something 4 pi into 10 to the power minus 7. What is I? Is a 3 ampere. 2 times A is 0.4. So let's calculate this. Get cancelled. It's something 0.1. If it is going in numerators, is plus. So we get 10 to the power minus 6 over 3 pi divided by 2. So 314 into 3 is something 9.42 around this. So here we say 9.42 into 10 to the power minus 6 divided by 2. It's around something C. It's something 4.17 to 10 to the power minus 6. The unit is a Tesla. Clear this? Hello. Good morning. Where are you? Hello. Clear this point? Okay, Shruti. Okay, Parikshit. Now, so in the today's session, we learn first magnetic field due to straight conductor. The formula is mu naught I over 2 pi r. Then magnetic field due to arc or any circular loop is mu naught over I theta times 4 pi r. Then we learn magnetic field due to circular or loop at axial point. Axial point in the sense this is a circular loop and this point is called as a your axial point. Axial point. So we have a formula something mu naught I over a square divided by divide by 2 times x square plus a square raised to power 3 by 3. And then similar manner we say at in this section at a center, that means your x will be 0. So your magnetic field is mu I over 2a. So this formula is very important as per your competitive exam purpose. Clear this point? So now we will assign to you class assessment. Let's see your class assessment part. It is visible to you, guys. With the help of this formula, you are going to are able to solve all your assessment problem. If you have any query, ask me. So start your assessment now. Parikshit, this is visible to class assessment. Okay, start. as per your class assessment, there's a one question. It's related to your basic. So please see. If you are not able to answer, just see guys. We know that what is a flux. So flux, if it is an electric, we say E dot ds is a flux. So similarly, for magnetic, instead of E, just use B. So your magnetic flux is equal to B into A. So what is your B, friends? So B is nothing but your current in a conducting wire, which is a solenoid. So in the solenoid, we use a magnetic field. B is equal to mu naught Ni, which is very basic. And the N is called as a number of turns per unit length and volume sometimes. So it is simply B is equal to mu naught Ni upon L. So this is your flux. Clear this? So this is your basic formula, I know. This is apart from here. So just use this formula. Okay? Or also get first question answer. Hello. Any problem in the first question? Just apply this formula on your white screen. So get the answer. Hello. Able to solve second question or not? All of you solve question easily, no problem. Any problem in the any question? Hello. Any problem in any question? Okay. Do it then. Okay, so unmute yourself and tell me what's the problem. Rajiv. The first problem, okay. Tell me. Hexagonal, if I'm not wrong, the question is related to your hexagonal. Rajira, this question is related to hexagonal. So tell me what's the problem. It is not possible to unmute yourself. Just write and say what's the problem actually you face. Yes. Yes.
Ma'am, am I audible?
Yeah, dear.
Ma'am, the fourth question, I didn't know how to proceed the sum exactly.
Okay, no problem. I will just say, just listen. Question is like a current I flowing in a hexagonal coil of side L. The magnetic induction at the center of a coil, right?
Yes, ma'am.
Okay. The question is about the is hexagon. See, this is your hexagon. Am I right? So the current is entering from here, and they want to know what is the magnet. They want to ask what is the magnetic field at the center. So for that, you should draw first of all corners from here. You get a center point like this. Getting? This is here also completed. So like this. So at the center, you have a magnetic field. Clear this first of all? Now,
Yes, ma'am.
see, this is your A point. If this is your A point, so consider any point. This is your A point. This is your A point. So this is your half of that A. If I put a perpendicular from here, see like this. So this is your A by 2 and this is your A by 2. Similarly, if this is your A, all points at the center are equal distance. Am I right?
Yes, ma'am.
So according to this, if you remember, I said if we have any line and we have two angles, one here, let's say here, and another one here, let's say theta. So we use a formula mu naught I over 4 pi r. What is the formula? Sine theta 1 plus sine theta 2, right? Am I right?
Yes, ma'am.
So see, at the center, this is a this triangle is behave like an equilateral triangle. So all the triangles is a equilateral. So what is the angle for this? It's 60. So for that, if I draw as a perpendicular, that is a perfectly at center, this angle will be 30. This angle is also 30. So see, if I put mu naught I over 4 pi r here, sine 30 plus sine 30. So what is the sine 30? Sine 30? Sine 30 is simply 1 by 2. 1 by 2, 1 by 2 is 1. Am I right? So from here we get mu naught over I upon 4 pi r time 1. First of all, clear this point?
Yes, ma'am. Clear.
Okay. Now see, the distance is about to distance. Your distance in the question is not given. It is safe at the center. So if we take a distance, at that time we know what is the actual distance. So we should calculate like this. If this is your distance, this is your triangle, this is your A, this is your A, this is your A by 2. So you should calculate this distance, which is nothing but A is equal to under root of A square minus A square by 4. Am I right? By Pythagoras. So when you solve, it's simply your 3a square by 4 in a root, or we can say A by 2 under root of 3. So this is your radius of the point. So what your formula you got? You got mu naught 4 pi I over theta. Sorry, not I over theta. I think I write here. Okay. Okay. So what you get? You get simply mu naught I into 1 upon 4 pi r. And here r, instead of r you write this. So you get mu naught I over 4 pi a root 3 over 2, then solving 2 mu naught I over 4 pi a root 3. Clear this?
Yes, ma'am. Got it.
Okay. So this is your magnetic field due to B1 point. So like that, you find all magnetic field and just add up. So your option A will be correct. Clear, dear?
Yes, ma'am. Understood.
Very good. It's okay.